Okay, let's look at this it's Virgin Orbit. It's called Virgin Orbit. And the idea is to take a payload and get it into low Earth orbit or even beyond later on, and not launch it from the surface of the Earth. So here's a normal rocket launched from the surface of the Earth, and it goes into low Earth orbit. Right there, that's some altitude. And the idea in the Virgin Orbit is to launch it from a 747. So this 747 has two things that it does differently. One, it's flying fast. I didn't find the actual speed of this modified 747, but I got this 900 kilometers per hour velocity for other 747s. And the launch height is 11,000 meters approximately. So how much energy do you save by doing that versus launching from the ground? Okay, so we got a lot of stuff to talk about here, and I'm going to do it all because I care. So let's first think about a normal launch right here. In order to be in orbit, there is one force acting on that, and we'll call this a circular orbit with a radius lowercase r. There is the gravitational force pulling down on that space object, whatever it may be. If it is in a circular orbit, then the magnitude of this force, I can use this for the F net, is going to be the gravitational force Fg, and that's going to be mv squared over r. So m is the mass, v squared over r is this acceleration for an object moving in a circle. And I didn't write these as vectors because they have to be in the same direction since it's the only force acting on it. But there you have it. That's the gravitational force, mass, the orbital velocity divided by the orbital radius, not the orbital altitude. Now, if I have two objects, the gravitational force would be g, the gravitational constant, times the mass of the object times the mass of the Earth divided by the distance between them squared. So this gives me a limit on the velocity, how fast you have to go in that orbit of radius r. So let's solve this for v, and you'll notice here the mass cancels, and I get v, and this cancels, is going to be the square root of g, mass of the Earth, over r, where r is the radius of the orbit, not the altitude. So I need to get this to that velocity. That means a change in kinetic energy, where kinetic energy is going to be 1/2 mv final squared minus 1/2 mv initial squared. Because there's two kinds of energy here. I need to deal with kinetic energy, and I need to deal with gravitational potential energy. So that's my change in kinetic energy. What about my change in gravitational potential energy? Well, gravitational potential energy, UG, is going to be negative g, mass of the object, mass of the Earth, over the radius. This comes from the work energy principle. It's negative because of a change in potential. This is a change in potential with respect to infinity. And the negative sign is basically the opposite of work done by gravity. And I don't want to go into too much details because I don't want to have a 5-hour-long video. Okay, so my change in gravitational potential energy is going to be delta UG. Is going to be the final potential energy, which is going to be negative g, mass of the object, mass of the Earth, over the final position. And this is going to be equal to, I'll just call that r. And then minus the initial, which is going to be plus g, mass of the object, mass of the Earth, over the radius of the Earth. So these two added together is going to be my change in energy, change in kinetic, plus change in gravitational potential. So that's a basic orbit. Now, what's different about the Virgin Orbit? Number one, it's not starting from initial velocity of 0. It's not starting on the radius of Earth. So both of these things change. And so I want to find the change in energy to get this 100 kilogram object. Did I write that down? Let's see. M equals 100 kilograms. That's my payload. From here to orbit, and then from the Cosmic Girl, the name of the 747, into orbit, and make a comparison. Now there is one thing. This is moving at 900 kilometers per hour with respect to the surface of the Earth, but the Earth is already moving. Okay, I don't know if you know this, but the Earth rotates with some angular velocity omega. So just from the fact that it's on the Earth anyway, it has a velocity that's not insignificant compared to this. So I want to include that. Now I'm not including the one other benefit that we have for Cosmic Girl, and that's air drag. So because it starts up higher, the density of air is lower, and you don't have to waste energy pushing through that air. So I'm not going to take that into account in this calculation. This will still give us a rough guideline for where we are with these two things. So let's go back to launching from Cape Canaveral. And the location does matter. Okay, so let's draw another picture because I need to find the initial velocity of an object on the Earth. So here's a side view of the Earth. And then here is the equator. And then this is the angle theta. And that's my object that I'm launching from. And I'm not sure. I know I live in Louisiana where this theta is about 30 degrees. I'm not sure. It should be close to that for Florida too. So if that's the case, if omega is 24, the angular velocity is 2 pi radians divided by the time of 24 hours. All right, that's the angular velocity. It's 1 revolution per day, and it's actually a little bit less than that, but that's fine. Because this is the rotation to get back to the sun, not the actual rotation. But it's all good. It's all good. And this, I'll call that R1. That's the radial distance of the object, right? Because it's not moving in a circle the size of the Earth. If it was at the North Pole, it'd be moving in a circle of size radius 0. So I need to find that. So I can say V1 is omega R1. That's going to be my angular velocity times the radius. And the radius R1 is this distance right here. So this is the radius of the Earth. So this is going to be R1 is the radius of the Earth times cosine of theta. And now I need to convert omega to radians per second. So I can multiply this by 24 hours divided by, in 1 hour, 1 hour divided by 60 minutes, right? This is a unit conversion. The hours will cancel and I'll get radians per minute. And I can do it again. 1 minute, 60 seconds. And then I'll get my angular velocity in radians per second. My R, I do need the radius of the Earth, which I can look that up. And this will give me my launch velocity. Okay, so then from that I can say delta E, let's call it Cape Canaveral, CC. It's going to be equal to the change in kinetic energy, and I'll call my my low Earth orbit A. Yeah, let's do that. So I get my change in kinetic energy, which is my final 1/2 m v squared. But remember, v squared is just this, right? So that's going to be times g times the mass of the Earth over the radius. The orbital radius is going to be RE plus A. That's it. Now, minus my initial kinetic energy, which is 1/2 m, and I'm just going to say this V1 squared. Now I need to add in my change in gravitational potential energy, plus, actually minus, G, the final, which is going to be mass of the Earth, over the radius, which is RE plus A, minus the initial, so it's going to be plus G M ME over RE. And that's the change in energy for launching from the Earth. And you can simplify this some because it has these terms come up multiple times, but I'm just going to leave it. Now let's do the same thing for the Virgin orbit. Yeah, that's what it's called. So delta E V for Virgin orbit. It's going to be the change in kinetic energy. It has the same final kinetic energy, 1/2 m g mass of the Earth over r Earth plus A minus the initial, which is going to be equal to 1/2 mv 747 squared. That's the velocity, which I need to convert to meters per second. Let's just do that. So this is going to be equal to, let's write it down here, v 747 is going to be 900 kilometers per hour. That's an hour. And then I can say there are 1,000 meters in 1 kilometer. And then I can say there are, in 1 hour, it's 3,600 seconds, which is 60 times 60. Okay, so I can do that. That's my change in kinetic energy. Let's put a box around this. And then plus my change in potential, which is going to be plus a negative g m me over re plus a, same as before. And the difference here is going to be plus g m me over re plus h, where h is my launch altitude. Okay, so I have two ways to calculate the change in energy, and now I just need to plug in all the numbers. So I'm going to switch over here to my favorite kind of calculator, Python. Let's just switch over here. Everyone likes Python, right? And you'll see I've already put in some of the values because I cheated, and I'm a cheater. Okay, I do need some other things in here. I need to convert this to the velocity to meters per second. So that would be times 1,000 divided by 3,600. H is fine. The mass is fine. Radius of the Earth. Omega, I need to convert that. So that was 24 times... Oh, wait, that was wrong. It's 2 times pi. And then I'm just looking at my notes right here. Divided by 24 times 60 times 60. And that's radians per second. Oops, I can get rid of those now. What else do I need? I got the velocity of that. Theta. Theta equals 30 times pi divided by 180. Convert that to radians. Mass of the Earth, I have radius of the Earth, A. A is, actually, I call that A. That's the launch altitude. And H is low Earth orbit, which is 400 kilometers. 400 times 10 to the third. Okay. So let's do DECC. I'm just going to type it in. So I'm going to say I'm just going straight from my equation. 0.5 times m times g times me. Make sure that you use the same case. Python's case sensitive. Divided by re plus a. That's the initial. That's the final kinetic energy minus the initial, which is going to be 0.5 times m times g. No. Times V1. I didn't calculate V1. V1 equals omega times, where did I put that? Times RE times cosine theta. And you'll notice here what's so great about this, right, is that I don't have to put that in here. I can just calculate V1 separate. That's what's great about Python. V1 squared. Squared in Python is star star. Okay, 2. That's my change in kinetic energy. And now I'm going to say minus G times mass times ME divided by RE plus A plus G times M times ME divided by RE. That's my change in energy for launch from Cape Canaveral. So let's go ahead and print that. Print energy. This is called energy. D change. Change in E for CC equals DECC joules. And let's save it because I didn't do that. Virgin orbit calc. Save. And I will give you the code. And I'm going to run it because you never know if you made a mistake, which definitely could happen. Nope, it looks okay. Okay. Now I'm going to do the same thing for the Virgin orbit. DEV equals, I could copy this whole thing, right? I shouldn't do that because I might make a mistake. But, okay, so because only some of the stuff changes. Okay, so I'm looking at this is the same. This is different, right? This is the V747. That's pretty good. That's the same. And then this is different. The initial potential is RE plus H. Print change in E for VO, Virgin orbit, equals DEV joules. Save it. Run. So, yeah, I saved, 500,000. No, that's still a lot. Let's see. Saving. Save is going to be DECC minus DEV. Energy saving is going to be save joules. Really, it should be the percent, but let's just run it this way. Okay, so I saved quite a bit of energy. It still requires a lot of energy. But the thing to realize is that energy is expensive when we're talking about this. We're talking about launching stuff. And this doesn't even account for the fuel needed to get up to the altitude of Cosmic Girl. So you have to have a bigger rocket to begin with to get up to that position. So there's more savings than this. It doesn't include the air resistance. It doesn't include the energy needed to move the fuel up to that altitude because we used a plane to get it up there too. But overall, it's still just a great example of using some physics to make some rough estimations and showing that Python is the best calculator ever. And I'll end there. I'll talk to you guys later.